Hello, physics students. So another topic that humans' knowledge of expanded dramatically in the 20th century or the 1900s is nuclear reactions. And that's the topic of today, nuclear physics. But we're actually going to spend 2 videos on this topic because there's just a lot of information. So today we begin Nuclear Physics 1. So first thing we want to get down is the notation that we use for representing elements. So nuclear notation, let's suppose we have element X. There's no such element, but let's suppose, there is one. Then what we do is we put the symbol like this and we put 3 numbers around it, A, Z, and N. Z right here is the most important. It's the number of protons in that atom, which makes it whatever it is. You could have different number of neutrons, but if you and still be a same atom, like carbon can have different number of neutrons, but if it changes the protons, it's no longer carbon. So this is the atomic number, most important. A up here, the number up here, is the total number of protons and neutrons together added up. So sometimes it's called the mass number, sometimes the nucleon number, sometimes the baryon number. And then the number on the lower right here is called the number of neutrons, and it's frequently omitted because we can find the number of neutrons from the other 2 numbers. Like for example, here, carbon, number 6, it has to be 6 to be carbon. If it's 7, it's not carbon anymore. But so carbon, 6, and then 14 here. So that tells me that there's 6 protons inside that element, inside that atom, I should say. How many neutrons are there? Well, the difference between those two, 14 minus 6, is 8 neutrons. So again, that's how we can omit that. We could put an 8 over here, but again, it's not necessary because you could find it that way. All right, so let me create a pause to give you a chance to copy these notes down. All right, let's move on. Now, there are 2 kinds of reactions that you can have when it comes to nuclear reactions. So let me just backtrack a little bit. So chemical reactions, like you studied primarily in chemistry, are when electrons are exchanged. So for example, sodium and chlorine elemental, when they react, what happens is the chlorine strips an electron away from the sodium. So now we have a sodium ion, a chlorine ion, we have salt. And so that's a chemical reaction. It's a transfer of electrons, but the nuclei in the middle of those atoms did not change. So we still had sodium, we still had chlorine after, because the protons and neutrons didn't change. But in a nuclear reaction, what happens is the nucleus actually changes. So one possibility is you have a big nucleus that breaks into smaller pieces. So this is one element and 2 completely new elements because they're going to split up the neutrons, the protons. So now if we change the proton number, we don't have the same thing we started with. So an example, let's suppose we've got a neutron-free bombard, smacks into a uranium, 92 protons, 235 total neutrons and protons together. And then that giant nucleus splits into 2 parts, a barium and a krypton. Here are the numbers, and then also 3 neutrons are now kicked out or are present after the reaction. So here's some things that are true of all nuclear reactions, including this one. The baryon number is conserved. In other words, if I take these numbers before, the 1 and the 235, I've got 236 baryons before the nuclear reaction. After, I've got 141, 92, and 3 times 1. So if you add these up, I got 236 here, and if you were to punch this on a calculator, you get 236 after. Charge is also conserved. If you look here before, the neutron has no charge, so 0, but the uranium has 92 protons, also neutrons, but they don't, there's no charge to neutrons. So let's just concern ourselves with the protons. So we got positive 92 here, times 1.6 times 10 minus 19. After, we've got 5636 protons and 3 neutrons, which have 0 charge. If you add these all up, you'll see that you have 92, positive 92 after, like we had before. But here's the thing, energy is not conserved. Mass is not conserved. And you may have heard that those things are conserved in chemistry class. Energy is conserved, mass is conserved, but in nuclear and actually even in chemical reactions, that's not true. the amount that they're not conserved by is so tiny, a zillionth of a percent, that we say, okay, that's same before and after, but technically not the case. But in nuclear reactions, the energies and the masses changes involved are suddenly significant, appreciable, so we can actually measure them. So mass energy, not conserved independently, but something called mass energy is. The two together are actually linked, and we'll talk about that in the next nuclear physics video, the next one coming up. But let me create a pause to give you a chance to copy these notes down. All right, there's a second kind of reaction. Let me make some room, I'll write it out. All right, so a fusion reaction. What happens? Things fuse. It kind of makes sense. You have one nucleus and another nucleus. Could be the same or two different nuclei, and they combine, stick together, and make one new atom, one new element. An example here, we've got hydrogen and then a hydrogen with a neutron stuck to it. So this is like a hydrogen atom, and this is another hydrogen atom, but an isotope of hydrogen. They smack together, and something's not right here. Let's see. Oh, sorry, no neutron here. A gamma ray. Okay, so two hydrogens coming together, sticking and making a helium, and then also a gamma ray, which is part of the electromagnetic spectrum, which is energy released. And also, I didn't write all these out because I already did, but 1 through 3, all these things are also true. For example, the baryon number is 3, and then 3 on this side. That's how I knew I made a mistake. I checked it quickly. So that's true. Charge is conserved. We've got +2 here and +2 on this side. And energy is not conserved. Mass is not conserved. Mass energy is conserved in this kind of reaction. So let me create a pause, give you a chance to copy this kind of reaction down. All right, so now let me just say this is something that humans mastered earlier. The first atomic bombs were these kind, fission, where uranium broke apart and made an explosion into smaller elements. Also, this is the kind of reaction that happens when you have a nuclear power plant. It's using some kind of fission, some kind of big atom that's unstable, falls apart, releases energy, and makes new, smaller elements. This came later. Humans did manage to create a fusion reaction in a hydrogen bomb, a kind of nuclear bomb. Boy, really devastating. Thousands of times more powerful than the bombs dropped on Japan. Like, I think it's like 3,000 atomic bombs in one when it's this kind of fusion reaction. Incredible. Anyway, people are trying to make power plants fusion type. It's kind of like people would say the holy grail of energy. If you could make a fusion reaction, it would probably solve the world's energy problems. You would need no more oil, need nothing. It'd be like almost limitless energy, because what you could do is you could take hydrogen, which is in water, like the oceans, fuse it into something bigger, and get enormous energy out of nothing but water. So obviously that's something people are interested in. All right, now some other related ideas, particularly with fission reactions. They happen naturally. Like, for example, there's carbon in your body that's radioactive. You're radioactive, I'm radioactive, your food is radioactive. And it's not because of pollution, it's a naturally occurring thing. That's how life is dated. When something dies thousands of years ago, we find a woolly mammoth, we do carbon dating because we're checking how radioactive it still is after many years, and we could figure out when it died from that. Radioactive stuff, there's radioactive material in most smoke alarms. It's a way you can detect smoke. So it's basically radioactive stuff all over medicine, and it's typically you have something that's naturally decays by itself. So how fast these reactions happens is a big important thing. That's what we're going to move on to next. So let me make some room over here. Okay, so half-life is defined as the time it takes for 1/2 of a sample to decay into products. So let me just pick an easy a number. Let's suppose I got 1,000 atoms. And then I wait, and in 2 years, I see that only 500 of them are left. So the half-life is 2 years because we went from 1,000 to 500. Now you might think that, okay, if it took 2 years for 500 of them to go away, wait another 500 years. Wait another 2 years, and the next 500 will be gone, you'll have nothing left. It doesn't work that way. Every time the substance decays, it loses half the amount after that amount of time goes by. So let's suppose, so one way to represent that with a formula is like this. So let's suppose we've got 1,000 atoms, and then the half-life is 2 years. After 4 years or 2 half-lives, we would have 1/4 of the amount. We'd have 1/2 to the second power, which is 1/4. 1,000 divided by 4 is 250. So in other words, half the substance is gone after 1 half-life. Another half doesn't go away completely. We just lose half of what we had here. So this is 500, now we've got 250. And then another half-life goes by. Well, what's half? Right around here. Another half-life goes by. Right there. And so the substance decays as a negative exponential function. So that's how the reactions happen naturally at their natural pace. So let me create a pause, give you a chance to copy this down. All right, this formula I put on here just for reference, but you don't actually have to use it because this is the way you could solve half-life problems on the Regents. Let me do an example here. Let me create some room, and then I'll write it out. Okay, so we've got a lab gets 12 moles of a radioactive substance with a half-life of 5,000 years. How much is going to be left if you left that sitting there for 25,000 years? So you could use this formula, as I said, but it's enough to just make a table solving half-life problems in the Regents. So what you could do is make a time column, and maybe I'll put M for moles, a mole column. And at time 0, when the lab got the substance, we had 12 moles. Now what I'm going to do is I'm just going to put increments of half-life like this. So 5,000. Another half-life would be 10,000. Another half-life would be 15,000. Another half-life would be 20,000. And another half-life would be 25,000. All we're doing is going up by 5,000s. So after 5,000 years, we went through 1 half-life. We'll have 6 moles left. Another 5,000 years, we'll lose half of that again. Another half-life, we'll lose half of that again. Another half-life, we'll lose half of that again. And another half-life, we'll lose half of that again. 375. And there it is. So our answer is there. So let me create a pause to give you a chance to copy this down. All right, so that's, again, as simple as the calculations are in the Regents regarding half-life. Create a table, just keep dividing by 2, dividing by 2, dividing by 2 till you get the answer. Now, this wouldn't work if we said, well, how much is left after 24,000 years? Ooh, okay, somewhere between these two. Then you need this formula. But like I said, on the Regents, always going to be an exact number of half-lives that go by. Now, the uranium that was used in the atomic bombs, I believe, has a half-life of 4 billion or 4 million years. Anyway, a long time. And so think about using that as a weapon. Imagine lobbing the bombs on Japan in the 1940s and saying, in 4 billion years, half this bomb will be decayed. Well, obviously, that's not going to be much of a weapon because it's so slow. It went boom, in an enormous explosion in an instant, in a fraction of a second, it leveled the whole city. So how did that happen? How did they make this thing that normally reacts so slowly react almost instantaneously? Well, you could alter the reaction rate by varying the density of the material. Packing a bunch together makes like a chain reaction. So that's what we're going to study next. So what happens is the reaction rates can be increased by increasing the concentrations. And then what happens is the particles ejected from one nucleus, rather than just flying out into space, they hit another nucleus. So it's kind of like you got this unstable nucleus sitting there and it gets whapped with a neutron or something like that, and then that shock causes it to break, ejecting its own radiation, which then flies into another nucleus, and so on and so forth, and you get these chain reactions happening. Now, you can speed it up just a little bit or a lot. So in a typical nuclear reactor, like when they're generating electricity, they have fuel rods. Now, these are just plastic cylinders, but imagine they're uranium, and a fuel rod out here is just ejecting its radiation into space. But if I surround that fuel rod by others, what happens when it creates radiation, it hits the other fuel rods, stimulating them to react faster. And so you can, when you pack these in like an array, all the radiation's causing chain reactions. But of course, that can get out of control. And so what you have to do is try and control that. So there are other rods of absorbing material called control rods. I'm going to use a piece of paper, but there are other rods that get lowered in, and they block the radiation. And the more you lower them in, the more they block. And so you could sort of move them around and cause, like vary the rate. Of course, there's all sorts of controls and safety mechanisms to prevent these fuel rods from running out of control. Sometimes they fail, like in Chernobyl, and then you get a meltdown, and then these fuel rods just go so intense that they start destroying the structure, the concrete structure all around. The metal gets melted, and you get out of control spewing of radiation. So that's kind of what's going on. The chain reaction got out of control, and humans were not able to keep it at a minimum. The extreme case of the chain reaction is when you take uranium or any other kind of material and you have just some explosives that blow it into a compact little ball. And then the chain reactions happen so dramatically, it creates a nuclear explosion. Okay, so it's all about increasing the concentration to get away from this usually slow reactions as determined by the half-life. All right, so let me create a pause to give you a chance to copy these notes down. Okay, so one more thing that we're going to do about the concepts of nuclear reactions today, and that's the types of radiation that are created. You know, obviously, when nuclear reactions happen, there's radiation, it's dangerous, it could cause cancer, it could kill you outright. So what are the kinds of radiation? What's hitting you when you're getting hit with radiation? So let me just jot that down, and then I'll talk about it. All right, so here they are. So the first one is what we call alpha radiation. Here's the symbol. It's a Greek letter from the Greek alphabet. So it's like the infinity sign with a quarter of it erased off in a sense. So that's alpha, how you write alpha. And what it is a helium nucleus. So that's 2 protons, 2 neutrons. And because it has the most mass and the most charge of all the kinds of radiation, it does the most damage. But it's also the easiest to stop. So think about, this thing, this alpha radiation hitting your body. It's like a cannonball, huge mass, a lot of charge, so it's going to really interact with your tissue and cause a lot of damage. But because of that very same reason, it's easy to stop, because whenever it hits anything, it's going to smack into all those atoms, and very hard for it to get through even a sheet of paper. So interesting. So you might be thinking, well, if it can't get through paper, it certainly can't get through my clothes. I'm not worried about alpha. Actually, there's a lot to be worried about when you ingest it, particularly like one example I could think of, you might have heard of radon gas. Some houses in the basement build up radon gas. Naturally comes out of granite. So if you have like a ledge under your house, you could have radon gas in there. You breathe that in, and then in your lungs, which are very sensitive and soft, this is basically decaying, and boom, boom, those alpha particles are bombarding your lungs, causing devastating damage. So alpha. Beta is, here it's a Greek letter as well, so it's kind of like a B, but you go like this, like a curly B. It's an electron, that's all. So a high-speed electron. It causes less damage compared to alpha because it's got less mass, less charge. But that means it's harder to stop. But still, because it's got the charge, when it hits anything, it's interacting heavily with the atoms that are there. And so a few sheets of aluminum foil could stop beta radiation. And then the last kind of radiation is gamma. Also a Greek letter, so it's kind of like the alpha turned on 90 degrees upward. What it is just a photon. You may have noticed it in the electromagnetic spectrum when we were studying, light waves in the waves topic. And so since it's a photon, it causes the least damage because it has no charge, but it also makes it the hardest to stop. So it can damage your body, certainly gamma radiation. You can't say, oh, gamma, I don't have anything to worry about. It could kill you, it could cause cancer, whatever. But because it has no charge, it can go through inches of lead. So imagine these, you can wear like some kind of suit or something. Not with gamma. If you had inches of lead suit, you wouldn't even be able to stand up. So it's very dangerous, very hard to stop. So those are the 3 kinds of radiation. I'll create a pause to give you a chance to copy this down. All right, so those are the concepts of some concepts about nuclear reactions. What you want to pay attention to is the kinds of reactions, how to determine, or right at the beginning, look at your notes, how to determine the mass number, the number of protons, neutrons inside a nucleus from the numbers that are around the element. You also want to know about the 2 kinds of reactions, fission, fusion. Basically, one breaks apart, one comes together. And then you want to know the 3 things that are conserved and not conserved about a nuclear reaction. Number of baryons is conserved, the amount of charge is conserved, but energy is not, mass is not. Together, mass energy, that's going to be in the next video. What does mass energy mean? Half-life, be able to do those calculations, dividing by 2 over and over again, and then know a little bit about, chain reactions and the types of radiation. So that's our video for today. I hope you enjoyed the video. I hope you enjoyed the physics. I'll see you in the next physics video.